your doubts and also Shreya your doubts. Okay. Just give me a moment. Yeah, so I'm sharing one of the questions sent to me as a doubt. Today's lecture also we will complete the doubts discussion in the first half an hour or so, and then we will go back to a discussion of fluid mechanics and properties of matter. Try to complete that portion today, or at least this week. So anyway, let's look at this question. Yeah, so the output characteristic of a transistor is shown in the figure. And this statement is given that the voltage across the collector emitter junction is 10 volts, and IC, there should not be 1C, there should be IC, is 4 milliamperes. Then the value of the beta parameter across AC is how much? Okay. So basically, you know that Ganesh, the beta parameter is basically what? IC divided by IB. Okay. So now it is given to us that it's operating in a situation when this is 10 volts, IC is 4 milliamperes. Okay. So these values here are giving me the base current. So let us see what is happening when this in volts VC is 10. So we are looking at this line. Okay. And IC in milliamperes is 4. So we are looking at this line. So we are looking at the intersection of these two. So the intersection of these two here is cut by what value of base current? So you can see the base current will be something between 20 and 30, no? Because the 20 graph is over here like this, and the 30 graph is like this. So the base current is greater than 20 microamperes but less than 30 microamperes. So beta accordingly should be greater than 4 into 10 raised to minus 3 divided by 30 and less than this. So see, beta can also be used like this. No? It's like a slope. So that's okay. Beta, when we say IC is equal to beta times IB. So as long as the biasing of the circuit is not changing, we can also say that delta IC is equal to beta times delta IB. Okay. So beta can also be explained as this thing for a particular value of BCE. So we can do that also. Okay, so near about this, you can see that your base current is changing from 20 to 30 as your collector current is changing from 2 to 4. Okay, so you can use that also, but basically it will be something in this region. So this can also be used. Understood, Ganesh? Okay. So shall I clear this? This clear? Okay. Just go back to another question. Yeah. So we move on to one more question. Yeah, so let's look at this one next. So which of the following will not be observed? We have to see when a multimeter operating in resistance measuring mode. So when a multimeter operates in resistance measuring mode is connected, basically what it does, it measures, it applies some voltage across the component and measures the ratio of voltage to current. Okay, so that's how it basically measures. So anyway, so the multimeter will be applying some minimal DC voltage across the particular circuit component across which you are measuring the resistance. Okay, and like that. So now we want that we connect it across the component and you reverse the probes. See, that actually you'll have to go through the physics lab manual, Ganesh, which will explain the working of the multimeter in detail, because the, you get a little bit lengthy over here theory wise. Okay. But as you know, the multimeter works in for both AC and DC and in different kind of modes. Okay, when it's measuring voltage, when it's measuring current, etc. So basically, you would have seen that to measure current, the prongs of the multimeter have to be placed around the wire, and it has some mechanism by which it measures the effect of magnetic field with respect to the current passing through the wire. Okay, whereas when it's measuring resistance, you have to connect the two probes across any device whose resistance you're measuring. So it's basically this part of your practical physics. Okay, so yeah, you have to go through the lab manual once. It's important for your JEE mains. Okay, that all the various experiments that are mentioned in your JEE mains syllabus, like from right from you know errors and this thing, vernier caliper and screw gauge, going up to the various experiments in each and every chapter, sonometer experiment, Kunz tube experiment in sound, then optics experiments, the UV method, optical bench method, all these things, terms like parallax and all that. In general, you should go through all of them because there will be one or two questions which are based on experimental physics and they will come from that section only. But at the same time, it is very lengthy going through them. The idea is that if you have done the experiments at some point of time in your 2 years of 11, 12, then you will know those terms anyway. It's not that you have to really memorize. The problem is for those who have not done the practicals or not, just attended physics lab. Anyway, so coming back to this. So here what is happening is when you connect the multimeter across a device to measure the current, if you reverse the polarity of the probes, so you're reversing the polarity of the DC voltage. So if the multimeter shows no deflection in both cases before and after reversing, if the chosen is a capacitor, this is not correct. Because when you connect a, this is not correct. Why? Because when you connect a DC voltage across a capacitor, okay, what happens is that the reactance of the capacitor is tending to infinity now. So it's like, so the current will be tending to zero. So it's not that it will show zero reading. Okay, it will not show no deflection. It will show maximum deflection because it's measuring the resistance now. So it will go out of scale. Whereas let's see what the second one is saying. Multimeter shows a deflection accompanied by a flash of light when the component is connected in one direction, and no deflection on reversing the probes if it is chosen. The chosen thing is an LED. Okay. This will happen because, as you know, a light emitting diode, the functioning of the light emitting diode is that it works on the voltage is connected across a junction, PN junction, that is semiconductor junction, in what kind of mode? In reverse bias mode. So that drift current that is occurring, No, sorry, that is light sensitive diode. In light emitting diode, that's photodiode. In light emitting diode, it has to be connected in forward bias. So in forward bias, what is happening is that the diffusion current creates electron hole pair recombination in the depletion layer, and the recombination of electron hole pair will release energy, which is in the form of a photon of a given wavelength, okay, according to the energy of the recombination. So whereas if you now reverse the polarity of the DC voltage you've connected, is going from forward to reverse bias, so recombination is not going to happen, so it's not going to emit. So this is actually a true statement that there will be a flash of light and it will show a certain amount of resistance when you connect it like this, okay, and there will be no deflection on reversing, okay, because you're connected it in reverse bias like that, okay. And the third one, multimeter shows no deflection in both the cases before and after reversing the probes if the chosen component is a metal wire. Again, see, this is a situation where the resistance is tending to zero, but no deflection means the resistance. So no deflection basically means that wait a minute. The problem here is, the multimeter doesn't have a deflection. It shows a digital reading. So the term deflection itself is a bit confusing here. But anyway, so if we mean that it does not show any value, that means it's showing a zero resistance. Whereas a metallic component will have some non-zero resistance. We know that metallic, it's only superconductors which have zero resistance. Okay, so there will be some amount of resistance. So that's why this statement is also, in my opinion, not true. It should show a very small reading because the resistance will be very small. If this statement is true, this statement is not true. This is a bit of a tricky statement because no deflection means it's showing resistance equal to zero. But metallic conductors do show some resistance, though very minimal resistance. Okay. And this is of course a correct statement. The resistance of a resistor is independent of the polarity of the DC battery. So this statement is true. This one is a bit contradictory if you ask me. By saying no deflection, okay, one thing they can mean that the amount of resistance is so small that it is below the least count of the multimeter. So it should show zero reading. But that's an erroneous reading. That's not correct. So again, out of all the statements, if it's a single choice question, the one that you can select best fitting is this. Okay, because definitely the capacitor will show a very high amount of resistance instead of zero resistance. It will block current altogether. So is it clear, Ganesh, this question? Uh, Bhumik, see, when you connect a DC voltage across a capacitor, now, your multimeter internally is basically a DC voltage. It's connecting with some kind of internal resistance also it has, and some kind of current measuring device through which it's giving the deflection and all that. So when you connect the capacitor, it blocks current. In steady state in the capacitor, the current will become zero. So the current is zero. It should show a very high resistance. It should not show no deflection. It should show very large amount of deflection, which will, basically, if you use a digital multimeter, it will show you an error because the current only is becoming zero. So anyhow, I hope this is clear. Okay, now I'm just moving on to Shreya's doubts. Just give me a moment. Yeah, so let's look at this question next. So in this, we have to now find the magnetic moment of the current carrying square loop, which has been kind of bent by 90 degrees, folded by 90 degrees. So Shreya, in this type of question, what you can do is you can use superposition. Okay. Suppose we have an imaginary current I here, which is like this. Okay. And another imaginary current I, which is like this. So the two are cancelling each other. Okay. So the effective current in this branch is zero. So now what happens? This one becomes a magnetic dipole moment, which you can see is clockwise when you see from above. So it has a magnetic dipole moment mu1, which is pointing like this, and this is clockwise when you see from here. So it is like this mu2. Okay. So if you take this as your system of axis, so you can see that your mu1 will be current into area. So that will be I into L square by 2 going into the plane downwards like this. So that's along the negative y-axis minus j cap, and mu2, the one which is in the xy plane, that will be again I into L square by 2, but its unit vector is going into the xy plane, so it is along minus k cap. So mu will just become mu1 plus mu2. So they are perpendicular to each other. So magnitude will become square root of mu1 square plus mu2 square. So that will be I into L square by 2 root 2, or you can write that as IL square by root 2. Now you can compare this with the original value of mu when it was a, I mean, they've taken it as m instead of mu. I've taken it as mu. So originally m would have been for just the square loop like this now, without the bending. So L by L. So m would have been I into L square. So this is by root 2. So it should be this. Is it clear, Shreya? Okay. So you have to remember that magnetic dipole moment is a vector quantity. So whenever you have a combination of materials like this, which are creating magnetic dipoles in individual planes. So for each plane, the magnetic dipole moment has a particular unit vector, and you have to do the vector addition. That's the general method. Okay, now let's move on to the next question. Just a minute. Yeah, so this is this type of question. So you have a plutonium atom which consists of a proton and an antiproton. So a proton is basically having charge plus C and mass of 1 atomic mass unit. Antiproton has a charge of minus E and mass equal to 1 atomic mass unit. It's the antiparticle of a proton which has charge plus E and mass equal to 1 atomic mass unit. So an antiproton is a negatively charged particle but with the same mass and modulus of charge as those of the proton. Now, if the binding energy of an electron in the hydrogen atom is this much, okay. So binding energy of the electron in the hydrogen atom means that this, okay, minus 13.3 हो गया है, whereas it's actually 13.6. And mass of the atom is 1800 times the mass of the electron. Find the energy of 3 protons emitted in transition. Find the energy of a 3 proton emitted in transition of a plutonium atom from, no, I think there's something wrong over here. This should be photon or something. Because transition of plutonium atom from first excited state to ground state, this will emit photon, not proton. So just change this instead of, okay, because this doesn't make sense. Protons will not be emitted when the transition like this happens. It's photons which will get emitted. So find the energy of a photon hona chahiye. According to me, it should be a photon emitted in the transition of plutonium atom from first excited state to ground state. Okay. So what is the difference between plutonium atom and hydrogen atom? Hydrogen atom, it has mass of 1 atomic mass unit. Okay. And plutonium atom, has a mass of 2 atomic mass units, but Z of 1 only. This also has Z equal to 1. So what we have to remember is the relation of energy with respect to these two things. No? It is so how it is affected by the mass of the nucleus. You have to understand that, and how it is affected by the charge of the nucleus. You understanding, Shreya, what I'm trying to say? I'll discuss the solution, but you have to understand that in comparison to the hydrogen atom, what are the energy levels of the plutonium atom? And why are they different? It has the same Z because there's only one proton, but it has double the mass of the nucleus. So how that is going to affect? Okay, so that's the thing we have to understand. Okay, so I'm just switching to my screen. So if you look at Bohr's model of atom, you have m is mass of electron, not the mass of the nucleus. So you have Ze square upon 4 pi epsilon naught r square is mv square by r. Okay, and the energy is half mv square minus Ze square upon 4 pi epsilon naught r, and you have mvr is equal to nh by 2 pi. So you can see that this entire derivation, it is independent of mass of the nucleus. It only depends on the charge of the nucleus and the mass of the electron. Is that correct? Okay, Aditya, I will come back to your question later. So in this, you can see that in the derivation, it is independent of the mass of the nucleus. It only depends on, okay, so this value that we get now, minus 13.6 into z square by n square. Okay, this is independent of mass of the nucleus. Okay. But I think the meaning of this question is somewhat different, because what they exactly mean, okay, I'm just going back to the question for a moment, because what kind of atom they are exactly talking about, because it consists of a proton and an antiproton. So the charge of the nucleus is becoming zero. Saying plutonium atom consists of a proton and antiproton. I think there is some lack of clarity in the question. One thing it could mean that instead of the electron orbiting the nucleus, you have the plutonium and the proton, which are in that, mutual orbital motion with respect to their center of mass, because they have same mass. So it could mean that, but then it's a much more complicated and lengthy question. So the only way I can interpret the question Shreya, where is this question from? Because the only way I can interpret this question now is that we have the proton and we have the antiproton, which are in this kind of mutual orbital motion with respect to their center of mass. And in this kind of mutual orbital motion with respect to center of mass. Okay. So, here what will happen is if the distance between them is r, that's one equation. And the energy of the system will be this, and the angular momentum of the system will become 2 times and omega we can put as, see, this whole distance is r. So this has orbital speed v like this. The orbital radius is r by 2. So v has to be substituted as omega r by 2. Yeah, so we can just write this as, so from this we will have to develop the formula for E. Okay, and from that compare the first excited, I mean the ground state, the first excited state. Okay. And from that get the difference in the energy levels as the energy of the photon. So yeah, hope this is clear to you. Okay, somewhat it is a easy example of the case of, like the equivalent in electrostatics of binary star system in gravitation. But if both the stars are of same mass, then it's very easy. You don't have to really use the reduced mass formula and all that, and do it directly. Okay, let's come back to another question now. Okay, so let's look at this one next. So an electron mass charge given jumps with with negligible velocity from the negative plate of a parallel plate capacitor connected across an EMF E. The speed with which the electron will hit the positive plate of the capacitor. Okay, so this is the negatively charged plate. It's connected across a voltage V. Okay. So if an electron starts from here at U tending to 0, so by the time it reaches here, it has a speed v. So the kinetic energy of the electron is going to be charged into voltage. So v should be equal to. So this is a pretty simple question. Is there a problem with the answer key or something? Because you have to just understand that work done by the electric field on a charge q is q delta v, no? I mean minus q into delta v, but magnitude wise it will become that much more. Delta u is equal to minus q into delta v, and this is negative of, sorry, is q into delta v. And this is negative of work done by the internal conservative force. Okay, so you understood now, it is a very simple question. Electron is moving across a voltage of v, na? So the work done by the electric field on the electron will be E into v. So that becomes the kinetic energy of the electron. Okay. Okay, let's look at the next question. So we have the relationship between the power consumed by a resistive load of variable resistance. Okay, so it's a variable resistance directly connected to a generator. It varies with the value of resistance according to this thing, according to this graph. So we have to find the EMF, internal resistance, etc. Okay. So basically this corresponds to this kind of a circuit diagram, that imagine you have connected a load resistor across a generator, which you can treat for this thing like a DC source, which has some EMF and some internal resistance. Okay. So the power consumed by the load resistor is I square R. So that is E square capital R upon R plus small r whole square. Okay. So as you know, this is maximum when capital R is equal to small r. Maximum power theorem. Remember that, Shreya? We can just apply that over here. So maximum power occurs when the load resistance is equal to the internal resistance of the battery. So just apply that maximum power theorem over here. So the power consumed by the load is given by this formula. This is the power consumed by the load. It's given by this formula. Now when you apply maximum minimum on this, you can see that for a given cell of EMF E and internal resistance R, if these two are given, then for what value of R you will get maximum power. So that will occur when this occurs. Okay. So here you can see maximum power is occurring when the resistance is 20 ohms. Okay, and that maximum power is equal to 500. So maximum power equals to E square upon 2 times R for the condition that capital R is equal to small r. So apply this over here, that 500 is equal to E square upon 2 times 20 ohms, because the internal resistance is 20 ohms, and we get the answer. Okay, let's move on to the next question. Just a moment, I have to share the question. Yeah. So go through this question, explain. So here you have to understand that there's a relationship between intensity and electric field amplitude for an electromagnetic wave. Okay, so E naught is electric field amplitude. Okay, and once you get that, the maximum potential difference will be equal to this electric field amplitude multiplied by length. Understanding is there? So what is this relationship? Do you know this? Okay, good. So, anything to do with EM waves in JEE mains is going to be formula based only. Nothing more difficult than that, because okay, so I think we're almost done with the doubts. Yeah, this last question. Yeah, just go through this, I'll explain. Okay, so see, in this question, the concept we have to use is that this base emitter junction is in forward bias, you can see. Okay. Now, since nothing else is given about it, we have to assume that it's a standard type of semiconductor junction. So in forward bias, the voltage, the what we call the voltage across the depletion layer, that voltage drop will be approximately 0.7 volts in forward bias. Okay, so to this 9 minus this minus IB into RB should be equal to 0. This EMF minus this. Okay, so upon IB is what is given to us. This is what approximately our resistance should come out to be. So whatever this value now, you can see it will be something greater than 2 but less than 3. So probably this should be the answer. I'm not doing an exact calculation, I'm just guessing it should be in this range. Okay, so this is a concept. All right, so that clears these doubts. I think I've just got one or two more doubts. I'll clear that. Okay, so let's go through this 27th question and discuss this. Okay, so satellite is orbiting around the Earth in a circular orbit. Initial magnitude of acceleration is this much. Okay, so magnitude of the acceleration is going to be equal to orbital velocity squared divided by this. Okay, and we know that the formula of orbital velocity is square root of, okay, this. So you can correlate this one with this. Okay. Now rocket is fired in the direction of the motion of the satellite from the satellite, due to which its speed and instantaneously becomes half of the initial speed. Okay. So if this was the orbital speed of the satellite, now we fire a rocket tangentially. So on firing the rocket, what happens is that the satellite speed becomes half because the rocket has been fired from it, going off in this direction. So the moment the satellite speed becomes half, you can see that it will now go in a different kind of orbit. It will go into an, okay. So just after the rocket is fired, the acceleration of the satellites has a magnitude of E2. So that acceleration will be the same because just after it is fired, mass of the rocket is negligible. Or anyway, that doesn't matter. The gravitational field at that point is the same. What changes is the radius of curvature of its path. The radius of curvature of its path will change because, or its path will actually not become like that. It's less than the orbital speed, so its path will become like this. It might hit the Earth also. Okay. So I'll just explain this in my whiteboard. Just give me a second. Yeah, so see what's happening is that at the moment when you fire the, just before firing the rocket, okay, it has an orbital speed which is square root of gm upon r, radius of the earth plus h. Okay, so it's in a circular orbital path, and it has an acceleration a1, which is, and that's only equal to, okay. Now after just firing the rocket, just at that moment only, still at the same height, but its speed has reduced to v naught by 2. Okay, so because it's at the same height, the acceleration will be the same. The gravitational field there is the same. Okay, but this acceleration is no longer equal to v square by r. Right? So v has become less than the orbital velocity. So it will go on this kind of a path now. It may or may not collide with Earth. That we'll have to check. Okay. So understood this, Aditya? The acceleration remains the same, but the path will change, and it's possible to calculate the properties of the elliptical orbit using angular momentum conservation and all that. But yeah, that's not really necessary for the given question. What's asked in the question is E1 by 2 ratio. No external force other than gravitational force. So that should be 1. Alright, so with this I've finished the doubts for today. Uh, so we'll just take a quick 2-minute recess and we will start with fluid mechanics and properties of matter. Try to complete that. So last time we had discussed hydrostatics, buoyant force, Archimedes principle, pressure gradient, all these things. So today we'll discuss about the second part of fluid mechanics, that is hydrodynamics, Bernoulli's equation, continuity equation and its applications. And then from there we'll move on to properties of matter, elasticity, surface tension, viscosity. Ashish, you have also sent some doubts. Okay, I'll take a look at them. Okay, so I'm sharing the doubt that Ashish has sent. So we have two Zener diodes A and B having breakdown voltages of 6 volts and 4 volts respectively. They are connected as shown. Output voltage VO, variation with input voltage linearly increasing with time is given. Aditya, you have sent me which doubt? 27th question. I just solved it for you. Which question you want to discuss now? Okay, anyway, let's look at this question first. Oh, that one. Okay, okay. I'll come to that. Okay. Okay, now let's look at this question first. So now there are some options given for this. So let's understand that also. So first go through this circuit diagram. We'll understand. So remember that diode 1 has a breakdown voltage of 6 volts and diode B rather Xenon diode B has a breakdown voltage of 4 volts. Okay. So when we apply some input voltage over here, we'll obviously assume we are applying it in reverse bias mode like this. So this is the input voltage. So if the input voltage is less than 4 volts, neither of them are in breakdown mode. So neither of them are going to conduct electricity. So V input is less than 4 volts. So both are in the normal working condition, like they're not in breakdown mode. So they're in reverse bias normal working condition. So what happens in reverse bias normal working condition? There's hardly any current. So the current in the circuit will take this kind of path. Take this kind of path. So I will become equal to V input divided by RL. Okay. So our V output will be equal to I into RL. So that will be equal to V input. Okay. So when we are looking at V output versus V input up to 4 volts, we know that it will be a linear graph like this, because hardly any current will go through A and B. Okay. This part is clear, Ashish? Okay. Now let's see what happens in the next situation. So if we make the current, rather the input voltage greater than 4 but less than 6. Okay, so if that is happening, then this one is still not conducting, but this one starts conducting. So this I breaks into I1 and I2. So this 100 and 400 come in series. So I2 will become 1/5 of I. Okay. So accordingly, you will see that we'll get output voltage, which is I2 into RL. So that will be still equal to V input. Okay, so it will continue to be a series because this branch and this branch are in parallel. So this is clear now. Okay, but what happens when the voltage is V input is greater than equal to 6 volts? Then whatever current I'm sending, okay, I mean there will be infinite current going through this. This becomes almost like a zero resistance path. So this output voltage okay, so what happens when this diode is also in reverse bias? The voltage across this junction, let's say this is CD, this becomes fixed. V output, the voltage across this becomes VCD, which becomes 6 volts, because that is the reverse bias voltage. Okay. Because remember, in reverse bias, the reverse voltage versus the reverse current, the moment you cross this, the voltage becomes constant, independent of current at the breakdown voltage. So it should become fixed at 6 volts. So now if I look at your output voltage versus input voltage. Now the input voltage is varying linearly with time. So whether I look at input voltage or whether I look at time is one and the same thing. Okay. So till this is 4 volts, this should be equal to input. Okay. Till it is 6 also, it should be equal. Okay. So it should be this way. But the moment the input voltage becomes more than 6, this becomes capped at 6. So that's how the circuit is working as a voltage regulator up to 6 volts. Is the question clear, Aditya? Sorry, Ashish. The question is clear. Okay, so between 4 and 6, let me explain what's happening again. So when this input voltage is greater than 4 but less than 6, what is happening is this is in breakdown mode. Okay, whereas this is still not conducting. This is so if this is in breakdown mode, if this point is now C and this point is D and this point is E, you can see VCD will become fixed at 4 volts or whatever current is passing through this. Okay, but the voltage across the output, which is I2 into RL, is equal to VC minus VE. See this loop, this outer loop. Understood now? So that's still equal to input voltage. So this resistor here makes that difference because there is some current I1 going through this, which creates a voltage difference here. You can consider internal resistance also, it's okay, but it's a small internal resistance. Whether we should consider it as a negligible internal resistance. Dips the slope between 4 and 6. No, I'll show you the options which are given. Just a minute. So there is no dip in the slope. So as you can see, this is the yeah, there was some confusion in the question because 2 and 4 are identical. Okay, so that completes these doubts. We will move on to fluid mechanics and properties of matter next. So just take a 2-minute break to reorient. Okay, people, so let's resume. So as I said, we will come to the second part of fluid mechanics today, which is hydrodynamics. So in hydrodynamics, remember what we are discussing is steady or streamlined flow of an ideal fluid. So ideal fluid, we've already seen the definition last time, that it is incompressible, which basically means that it has a uniform density independent of pressure. The density should not change with pressure, so it should not be compressible, or its compressibility factor should be negligible. And secondly, it is non-viscous. Okay. So basically, the coefficient of viscosity is tending to zero. So there is no non-conservative force, no non-conservative drag force kind of thing, which is important in our application of hydrodynamics. Now, let's also understand what is the exact meaning of steady motion or streamlined flow. So steady flow is a type of flow wherein any volume element, okay, undergoes a translational motion. That is, it is irrotational. It does not have any rotation happening. And a direct result of that consequence is that any fluid element at a particular point or at a particular cross section has identical velocity to an element, a volume element or a fluid element, just before or after it crossing that point. So what that means to say is that if we're looking at a flow of a liquid through a tube like this, then at a particular cross section, any fluid element will have a velocity v such that next moment another fluid element will come and occupy that point. It will have the same velocity as the one previously, or just previous to this moment some other element had occupied that position at that cross section. It would have the same velocity as the one right now. So at a particular cross section, there's a fixed velocity for every particle that passes through that point. Okay, so those are the properties of the streamlined motion. So as a result of that, what happens is that in steady flow or in streamlined motion, the liquid molecules, they follow well-defined paths, which we call the streamlines. Because at every point, the velocity vector, at every cross section, the velocity vector is a fixed value. So if we draw tiny velocity vectors and join them together, they will show the trajectory of the fluid particles. And these trajectories or these paths don't change with time. They don't crisscross each other because the motion is irrotational. So these trajectories or these paths are called the streamlines. Okay. They are fixed trajectories or paths along which volume elements of fluid flow, and they don't cross each other. Okay. So now based on this, we have two important equations for streamline or steady flow. One is called the equation of trajectory, equation of continuity. So as liquid is flowing through a tube of varying cross section, if at a particular position the cross sectional area is A1, and at another position the cross sectional area is A2, and liquid is, let's say, flowing in this direction, so the velocity of flow at A1 is V1 and the velocity of flow at A2 is V2. Okay, then you can see that in time delta t or dt, the volume of fluid entering, in my diagram, entering from the cross sectional area A1, that will be delta V equal to A1 V1 delta t. Okay. And similarly, the volume of fluid exiting this region in between A1 and A2 from cross section A2, that will be A2 V2 delta t. So we have, because the liquid is incompressible, there must be a fixed amount of volume of liquid in between these two cross sections. So A1 V1 delta t must be equal to A2 V2 delta t, okay, which is the volume rate. So basically what equation of continuity says, that delta V by delta t, the volume rate of flow, is same at all positions. A1 V1 is equal to A2 V2. So this is our equation of continuity. But if we compare any 2 points where the area of cross sections are A1 and A2 and the velocity of flow are V1 and V2, then A1 V1 must be equal to the product of A1 into V1 must be equal to the product of A2 into V2. So this is called the equation of trajectory. Sorry, the equation of continuity. And what it basically means is that there is a uniform volume flow rate. Volume rate of flow throughout the liquid in steady flow. Okay, delta V by delta t, the volume rate, this is uniform, and that is equal to the product of area of cross section into velocity of flow at any given point. Okay, so this is one important equation. And along with this, the second equation that we use in steady or streamlined flow is called the Bernoulli's equation. So Bernoulli's equation is a type of application of work energy, you can say, for an ideal fluid in steady flow. So imagine we have a section of an ideal fluid which is in steady flow like this. Okay. Where the velocity of flow at this point is v2, the velocity of flow at this point is v1, and with respect to some reference level, this is at a height h2 and this is at a height h1. Okay, so if we apply work energy theorem to this section of liquid over here, this section, just imagine a body of liquid, the volume of liquid. Now it is being, so if the internal pressure here is P1 or P2 here and P1 here, so it's being pushed from this side with a force of P2 into A2, and is being pushed from this side with a force of P1 into A1. And in a small time, if this is the situation at T equal to T, then a small time later, it would have got displaced like this, where this would displace by V2 delta T and this would displace by V1 delta T. So the net work done should be equal to the change in kinetic energy plus the change in gravitational potential energy. So net work done by external forces on this, you can see P2A2 is doing negative work. Okay. Whereas P1A1 is doing positive work. Okay. This should be equal to the change in kinetic energy plus change in potential energy. Now, how we'll calculate the change in kinetic energy? So for that, just understand that in time delta t, what was here earlier is now coming to this kind of position. Okay. So that means this much mass has got added into our system because the liquid is flowing like this, whereas this much mass here has got subtracted. So this mass is moving at a speed v2, this mass is moving at a speed v1. So this is mass delta m1, this is mass delta m2. So you know that delta m1 is equal to delta m2 is equal to density into a1 v1 delta t, which is density into a2 v2 delta t. So you can just write this as density into some amount of volume of liquid which has moved. So the change in kinetic energy will be the kinetic energy of this portion minus the kinetic energy of this portion. So it will be, I'll just relabel this 1, this one 2. So this mass has got added. So its kinetic energy has got added half delta m1 v1 square, and this mass has got subtracted. So minus half delta m2 v2 square. Now substitute this here. So the change in kinetic energy is half rho delta v into v1 square minus v2 square. So this term will now go over here. Okay. Whereas this term also you can see, we can write it as P1 minus P2 into delta V over here, because again A1 V1 delta T is equal to A2 V2 delta T, which is the change in volume delta V, the amount of volume which is flowing. So this should be equal to the change in kinetic energy plus the change in gravitational potential energy. Now likewise, the change in gravitational potential energy, what will be that? It will be the potential energy of this section, which is at a height of h1, minus the potential energy of this section, because this section has got added to our system, this section has got subtracted. Okay. So it will be delta M1 GH1 minus delta M2 GH2. So again, it is rho into delta V into GH1 minus GH2. So this is our delta U. So this term will get added over here. So now if we put together all this here, this equation becomes P1 minus P2 into delta V is equal to okay. It's actually the other way around. This mass is getting subtracted, this mass is getting added. So my mistake. These should be in reverse order over here. So this is getting subtracted, this is getting added. Okay. And likewise here also. This is getting subtracted, this is getting added. So we get this relation that P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. So this, as you know, is called the Bernoulli's equation. So we can relate any 2 points like this inside a liquid. So the sum of P plus half rho V square plus rho GH is constant within a flowing liquid as long as it's an ideal fluid in steady flow. That's another way of expressing Bernoulli's equation. So each of these terms has the dimension of energy per unit volume, okay, and they are scalar quantities, and we say that the sum of three heads is constant: the pressure head, the kinetic head, and the gravity head. It's like an expression of work energy where the sum of three heads, the pressure head plus the kinetic head plus the gravity head, should remain constant as long as the liquid is in steady flow. So just do a quick review of this. We will discuss the applications next. Okay, so let's understand a quick application of Bernoulli's equation. So for example, if we have a tapering pipe like this, okay, so this is basically continuing like this. So at this point, the area of cross section is 2 centimeters square. At this point, the area of cross section is 4 centimeters square, and there is water in steady flow. So the volume flow rate of water delta V by delta T is, so 50 cubic centimeters per second, 50 cc per second. Okay. So the velocity of flow here is V2 and the velocity of flow here is V1. So first thing is find V1 and V2. Okay. Second, if this height difference is h, if h is equal to, let's say, 10 meters and pressure at A2 is 4 atmospheres, then find pressure at E1. So we'll just see how we can solve this question by using a combination of Bernoulli's equation and continuity equation. Since it is water, so take the standard value of density of water, which is 1 gram per cc. Yeah, so that's correct, Aditya. We can see that by using the equation of continuity, A1 V1 is equal to A2 V2 is equal to the volume flow rate delta V by delta T. Okay, so V1 will become 50 cc per second divided by 2 centimeters square. So that is 25 centimeters per second. And V2 will be just become half of that. The area is double. 12.5 centimeters per second. So these are the velocities. Now next we will apply Bernoulli's equation. So we can see that P1 plus half rho V1 square plus rho g H1 should be equal to P2 plus half rho V2 square plus rho g H2. Now the pressure at the point having cross section A2 is given to us as 4 atmospheres. So P1 will become P2 plus half rho V2 square minus V1 square plus rho g H2 minus H1. So P1 will become P2 plus half rho. Now we can write this as you can see that V2 is equal to half of V1. Okay, so this will become 1 by 4 minus 1 of V1 square plus this will become rho g H because H2 minus H1 is nothing but that positive height. So P1 should be equal to P2 minus 3 by 4 or rather 3 by 8 rho V1 square plus rho g H. So in this now we should substitute everything with SI units. So rho should be 1000 in kg per meter cube. V1 should be 0.25 meters per second and H should be 10 meters. G should be 10 meters per second square. And P2 of course is given to us as 4 atmospheres. So P2 we can substitute as 4 into 10 raised power 5 pascals. So this calculation will now give us the value of P1. Okay. So this is about the standard application of Bernoulli's equation and continuity equation. So now, for example, the most common derivation done using Bernoulli's equation and continuity equation is the derivation of velocity of efflux concept. Okay. This is a standard formula you should know. So if we have kind of a wide vessel like this, an open tank kind of situation, with a small opening at the bottom. So we had a small opening here, the bottom, and it is filled with fluid up to a certain height. So on opening the orifice or the small opening over here, liquid comes out in an efflux. So the velocity of efflux, we generally denote it as VE. So this velocity of efflux, exact formula comes out to be square root of 2gh upon 1 minus a by a whole square. But we can approximate this as root 2gh, where h is this height and E is the area of the orifice or the opening here. Orifice means a very small opening, and capital A is the area of this tank's cross section. So it comes by applying Bernoulli's equation to these 2 points. If we take this as point 1 and just outside the orifice as point 2, so you can see that P1 plus half rho V1 square plus rho GH1 should be equal to, on the other side, P2 plus half rho V2 square plus rho GH2. Now here we can see that H1 minus H2 should be substituted as H. P1 should be equal to P2 should be equal to atmospheric pressure. And V1 into capital A should be equal to V2 into small a, where this V2 only is the efflux velocity. So on substituting all these things here, we will get this relation. Okay, and now because A by A is very small compared to 1, so 1 minus A square by capital A square is tending to 1. So we get this relation. So this is called the velocity of efflux or the speed of efflux. And this is the standard derivation that Bernoulli's equation is used for. Okay. So this is like the essential part of fluid dynamics or hydrodynamics. And there are a few more types of applications we'll discuss in the next lecture, but any type of question related to fluid dynamics or hydrodynamics can be solved by using this type of application, where we use a combination of the continuity equation and the Bernoulli's equation, like we've done with this today. Okay, so we will conclude today's session here. Next time we'll pick up fluid dynamics again. We'll do some questions and applications of this type again and complete hydrodynamics, and then we'll look at the properties of matter section. So I think we have a lecture on Wednesday and we can look to complete this on Wednesday. So Wednesday's class, we will start with this portion. If we finish and have time remaining in the end, then we'll look at doubts. But the priority on Wednesday will be to complete the properties of matter section. Okay, so that's it for today's lecture. People, wish you all the best. Yeah, Aditya, surface tension will be part of properties of matter. So properties of matter will be elasticity, viscosity, and surface tension.